Hello everyone, myself Dr. Vijaykumar, Associate Professor, Department of Electronics and Communication Engineering, Aditya University. In today's session, we are going to see problems on cross power spectral density. So, at the end of this particular session, students will be able to learn the definition of power spectral density and will apply the concept of the power spectral density in solving the problems. So, recalling the definitions of mathematical definitions of power spectral density. Power spectral density is basically nothing but the amount of power per bandwidth. So the cross power spectral density is a measure of amount of power distributed over two different frequencies of different random process x of t and y of t. So and mathematically the cross power spectral density is denoted as Sxy of omega is equal to Fourier transform of cross correlation function. And the power spectral density and cross correlation function form the Fourier transform pairs. They are related with the Fourier transform. And cross power spectral density is also mathematically defined as Sxy of omega is equal to limit tau tends to infinity expectation of xt of omega yt complex of omega, or you can write in other way expectation of xt complex of omega yt of omega by 2t and limit t tends to infinity. If I want to compute the average power, the mathematical formula for computing the average power with the help of autocorrelation is simply we need to substitute tau is equal to 0. Otherwise, integration of the power spectral density with respect to frequency gives the average power. So, there are some properties which we need to recall. One property is the power spectral density is an even function of omega, and this is the first property, and the real part of Sxy and Syx are even functions of omega. The imaginary part are odd functions of omega. And Sxy of omega is equal to 0, Syx of omega is equal to 0. It means that the random process x of t and y of t are orthogonal to each other. If x of t and y of t are uncorrelated and have a constant mean values, let us say x bar and y bar, then the power spectral density is equal to 2 pi into x bar into y bar del of omega. And this is the last property which is used frequently in the solving problems. Fourier transform pairs. Power spectral density is Fourier transform of autocorrelation function, and autocorrelation function is inverse Fourier transform of power spectral density. Very frequently we use for solving the problems. So let us apply the concepts of the definitions of cross power spectral density and the properties of cross power spectral density in solving the practical problems. So here one problem is given. Compute the cross power spectral density for a given cross correlation. So a cross correlation function is given to us. Now we are asked us to compute the power spectral density. We know that the property of autocorrelation function and power spectral density are related with the Fourier transform pairs. That relation is called Wiener-Kinczi relation. So if you want to compute the power spectral density, the power spectral density is nothing but the Fourier transform of cross correlation function. So the formula is given as minus infinity to infinity Rxy of tau e power minus j omega tau d tau. So applying this formula, we can compute the power spectral density, cross power spectral density. So substituting the cross correlation function here, we know that unit step function is defined only for positive values. So u of t is equal to 1 when tau is greater than or equal to 0. So I changed the limit 0 to infinity, from minus infinity to infinity, 0 to infinity. So e power a into e power b can be written as e power a plus b. And we know that the integration of e power minus at is e power minus at by minus a, and substituting the limits, e power minus infinity is 0 and e power 0 is 1, minus minus will be plus. So the Fourier transform of the given cross correlation function is 4 by alpha plus j omega, which is also mathematically equal to Sxy of omega. So this is the cross power spectral density for a given cross correlation function. Simply using the property, we can compute the cross power spectral density from a given cross correlation function. Let us solve one more problem related to cross power spectral density. We will apply the concepts and compute the cross power spectral density function for two random process. One random process given as x of t is equal to a cos omega naught t plus b sin omega naught t, and y of t is given as a sin omega naught t plus b cos minus a sin omega naught t plus b cos omega naught t, and given the mean values of the random process 0 and the variance of the random process sigma square. So now first what we will do is, first we will compute the correlation function, later on we will compute the power spectral density. So it will be very easy because we will use the Fourier transform pairs in computing the cross power spectral density, which will be helpful in writing the final answer. So what we will do is, first we will compute the cross correlation function. The cross correlation function is mathematically defined as expectation of x of t into y of t plus tau. Substituting the x of t and y of t and multiplying the so many 4 totally, we will get 4 terms. So this is one term, this is another term, this is another term, this is another term. So given that the expectations of the random process are given as 0 and expectation of AB, since they are statistically independent, expectation of AB is equal to expectation of A into expectation of B, which is also equal to 0, and the given the variance is sigma square. We know that variance is related as expectation of x square minus expectation of x whole square. So now variance of A will be simply expectation of A square minus expectation of A whole square. Given expectation of A as 0. So this is 0. So sigma square is equal to expectation of A square. Sigma square is expectation of A square. So we will substitute these things. So now the cross correlation function will be sigma square sin omega naught tau cos omega naught t plus omega naught tau cos omega naught t sin. So this is of the form sin A cos B minus cos A sin B. This can be written as sin A minus B. Doing that, what we will get is the residue term which is remained at the function is sin omega naught tau minus sigma square sin omega naught tau. So the cross correlation function is a function of tau. Rxy of tau is equal to minus sigma square sin omega naught tau. Okay. Now we can comfortably use the Fourier transform pairs in computing the cross correlation function. So the cross correlation function, we will apply Fourier transform. Sigma square is a constant I will bring outside. The Fourier transform of sin omega naught t is expressed as pi j or j pi into del of omega plus omega naught minus del of omega minus omega naught. So simply by substituting the Fourier transform pair, we can compute the cross power spectral density. So it's always convenient to apply the Fourier transform because the standard Fourier transform pairs are available to us. We can use those in computing the power spectral density. Let us see one more problem related to the cross power spectral density computation, and we will avail the Fourier transform pairs. So the cross correlation function, two cross correlation functions are given. One is a square by 2 sin omega naught tau, another one is a square by 2 cos omega naught tau. Let us compute the Fourier transform for these two functions. So a square by 2 sin omega naught tau. So the Fourier transform of this is simply j a square by 2 into j pi of del of omega plus omega naught minus pi into omega minus omega naught. This is actually deduced from this relation. So we can use this relation or directly we can use the Fourier transform pair of sin omega naught tau. Next, the Fourier transform of cos omega naught tau. The cos omega naught tau Fourier transform is pi into del of omega plus omega naught plus del of omega minus omega naught. We can use this relation. So the Fourier transform will be simply a square pi by 2 a square pi by 2 del of omega plus omega naught plus del of omega minus omega naught. So the major advantage here is we are using the Fourier transform pairs. So when we are solving these problems, we need to memorize the Fourier transform pairs of the standard functions like sine, cosine, impulse, unit step, rectangle function, triangular function, exponential function, and t into e power minus at. So like that, so many functions we need to remember Fourier transform pairs. So if Fourier transform pairs are known to us, we can solve these problems very easily. Next, now we will see the converse. The converse is when cross power spectral density is given to us, how to compute the cross correlation function. We need to apply the inverse Fourier transform pair concept. So the cross power spectral density is given in this problem is xy of omega is equal to 1 by minus omega square plus j 4 omega plus 4. This also mathematically written as 1 by 2 plus j omega square. Now we need to compute the inverse Fourier transform to compute the cross correlation function. So 1 by 2 plus j omega or 1 by a plus j omega. The inverse Fourier transform is e power minus at u of t. If it is 1 by a plus j omega whole square, the Fourier transform is t into e power minus at u of t. Okay. Now we will apply the same concept. Now 1 by 2 plus j omega whole square. Now this can be written as t into e power minus 2t u of t. So which is nothing but the cross correlation function. So the Fourier transform pairs play a very key role in the spectral characteristics of the random process. So regularly we use this Fourier transform pairs in solving the problems. And let us see one more problem related to the inverse Fourier transform. The cross power spectrum is given. Now we are asked to compute the cross correlation function using the inverse Fourier transform concept. So the cross correlation function, this is rxy of tau. The cross correlation function is the inverse Fourier transform of the power spectral density. Applying that a plus j b omega. Omega absolute value of omega less than means minus 1 less than omega less than 1. So minus 1 to 1, we can write this one a plus j b omega e power j omega tau d omega. So this a into e power j omega tau, integration of e power j omega tau is, here omega is the variable parameter. So e power at by a, here a is j tau, a by j tau e power j omega t minus 1 to 1. Similarly, here we will apply uv rule. So integral u dv is equal to v du minus integral v du, uv minus integral v du. So this is the formula we will apply. Here u is j b omega, dv is e power j omega tau. So v will be e power j omega tau by j tau. So here this is uv minus v du. Again we will substitute all the limits. Substituting the function will be something like this. We know that as per the Euler's relation, sin theta is equal to e power j theta minus e power minus j theta by 2j, and one more Euler's relation, cos theta is equal to e power j theta plus e power minus j theta by 2j. So using these two Euler's relation, we can modify this function in terms of sine cosine. This is e power j minus e power minus j by 2j. It can be written as 2a by tau sine tau. Similarly, this e power j theta plus e power minus j theta by 2. This can be written as 2b by tau cos tau, and this also in terms of sine. So applying the LCM, taking the tau square outside, a tau sine tau minus b sine tau plus b tau cos tau. So this is the 2 cancels out here. So this is the cross correlation function for the given cross power spectral density. Let us see one problem how to compute the power spectrum when two different random processes are involved and one random process is a function of another random process. Now see here, given a random process y of t is a function of another random process x of t into cos omega naught t, where omega naught is constant, x of t is stationary random process with power spectrum Sx of omega, then we need to compute the power spectrum of y of t. So first what we will do is we will compute the cross correlation function, later on we will compute the power spectrum of y of t. So the cross correlation function or autocorrelation function of y of t is ryy of t, ryy of t comma t plus tau is equal to expectation of y of t plus tau. So substituting y of t here and separating x of t terms, expectation of x of t into x of t plus tau is rx x of tau. Next cos omega naught t plus tau. Now this ryy of t plus tau is rx x of tau cos omega naught t plus tau. Now we are computing the time average autocorrelation function. So applying the time average autocorrelation function, this part will vanish. If you compute the integration for this one, integration of cos will be sin t minus sin t, we will get 0. So the term which is, the residue term which is available here is 1 by 2 rx x of tau cos omega naught tau. Now the power spectrum we can compute simply by applying the Fourier transform. So applying Fourier transform, rx x of tau cos omega naught tau. This can be written as sxx of omega minus omega naught plus sxx of omega plus omega naught. So given sx, so substitute here, we will get the cross power spectrum of y of t. One more problem is given in terms of cross correlation and cross power spectral density. The cross correlation function is given. So we know that as per Wiener-Kinczi relation, the time average autocorrelation function and the cross power spectral density are Fourier transform pairs. So whenever in general this kind of terms are given, we need to compute the time average autocorrelation function. Computing the time average for this one, what we will get is this term will vanish, sin t minus sin t, only this term will be present in the final term. So applying the Fourier transform for this one, ab by 2 1 by 2j. So sin for this one pi by j del of omega minus omega naught minus del of omega plus omega naught. So substituting final answer, we will get the cross power spectral density in terms of impulse function. Here also we availed the Fourier transform pair formula. So in this session what we have seen is we have defined what is meant by cross power spectral density, and we have also defined the properties of cross power spectral density, and finally we applied the concepts of cross power spectral density in solving the problems. So in the next session we will see the auto power spectral density and its properties, and we will apply the concepts in solving the problems. Thank you.